All right, so we kind of laid the groundwork for this little section here on different types of proofs.
Everybody vote for me by referendum.
Pizza every meeting.
All right, so when you're trying to prove something by a contradiction, you start by assuming the opposite of what you're trying to show is true. So in this one, we're trying to show that the square root of 2 is irrational. So what we're going to do is say it's rational. So we're going to say, suppose root 2 is rational.
We're going to prove by contradiction.
Okay, so this was statement 1. Okay, so we're going to assume the opposite of what we want to show is true. Let's see, suppose the... Yeah, you're right. Suppose the opposite of root 2 is irrational. All right. So by definition, if something is rational, so our second statement here is if something's rational, then you can write it as the ratio of 2 integers. All right. Is that what I did? Well, I didn't. Did you write it down already?
Yeah.
Oh. Oh. Okay. Well. Alrighty. Okay. Now, what allows us to do this is a rational number can be written as the ratio, as the relatively prime ratio. So that is important. Okay. A rational number, okay, can be written, okay, as the ratio of 2 relatively prime integers. Now, this is what's going to create the contradiction. Okay, so this is, let's see, this was 1, this was 2. Okay, now here's the thing that when a pair of numbers are relatively prime, that means they don't share any common factors. So that's what relatively prime means. The only number that you could divide into both P and Q would be 1. So there's, like you couldn't divide P and Q by 3. You couldn't divide it by 2. You couldn't divide it by 5. That's what the word relatively prime means. Okay, P and Q. Okay, the term relatively prime means P and Q don't share any common factors. Do not share any common factors, like a 2 or a 3. So like the ratio 3/5, that's relatively prime. I can't divide them by anything. 7, 9. They don't have to be prime numbers, but you can't reduce it. Okay, the fraction can't be reduced. Okay, so this is what this is where the contradiction is gonna come up. So as we go through this, it's gonna turn out that if what we assumed is true, then they're gonna have common factors. Therefore, what we assumed is true can't be true. All right. Okay, so the next step, square both sides. Okay, so we get 2 equals P squared divided by Q squared. It's the same thing. When I wrote non-reducible, that's relatively prime. That means the same thing. Okay, now what we're going to do, so that you understand where we're trying to go with this, we want to show that one of these numbers, one of these values, is an even number. Actually, we want to show that this has to be even and this has to be even. Okay, any even number, guys, if you just look up here, an even number is going to always equal 2 times some integer. Every even number can be written as 2 times a number. So what I'm going to end up, I want to get these so that they equal 2 times some number. All right, so my next step then is I am going to multiply both sides by Q squared. Okay, so the left side becomes 2Q squared and the right side becomes P squared. All right, now here's why this is important. We can now say P squared is an even number. Because it's equal to 2 times some other number. Okay, so since P squared equals 2 times some integer, okay, in step 4, we can say that it's even. That's how we can, because that's what an even number is. It's a multiple of 2. Even numbers are multiples of 2. Okay, now, if p squared is even, let's see, do I want to write it here? Yeah, I guess so. If p squared is even, then p is even. When you multiply 2 evens, you get another even. The square root of an even is even. That's what allows me to make that statement. An even times an even gives you another even. So that means p has to be even. So you see we established that p squared's even, so that means p is even. No, I don't. Okay. All right, now, p is an even number. So we've established that for p. Now what that means is I can write p as 2 times some number. So I'm just going to let that number be k. Okay, so step 7, the justification for it, okay, since p is even, I can write it as 2 times some number. Since p is even, we can write it as 2 times some number. It as 2 times some integer. That integer is represented by the letter k. Just like if a number was odd, okay, all even numbers can be written like this: 2 times some integer. All odd numbers can be written as an even plus 1. So every odd number can be written using 2k plus 1. All even numbers can be written using 2k. All right, so you now know, you see what we've done. We've shown that p is an even. Now, if I show that q is an even, then these two numbers would share a factor which would contradict what we highlighted here. So now I got to do the same thing and just establish that q is an even. And then if I have an even over an even, it would contradict statement 2 here. You could, yeah. But here's what we're going to do. I mean, there's lots of ways to do this. This is not the only way to prove this. Okay. All right. What I'm going to do is I'm going to take statement 7 and plug it into statement 4. So 2q squared equals 2k quantity squared. So if somebody was looking at my proof, I would say substituted seven into 4. So I took step 7 and I put it into step 4. So if I simplified that, that would give me 2k squared equals or 2q squared equals 4k squared. Okay, so I'm just going to say I do that substitution and then simplify. Okay, so then if I simplified this and I solved it for q, I'd have q squared equals 2k squared. So what can we now say about q squared? What kind of number is it? Yep. Right, so now we can say q squared is an even, and therefore q is an even. For the same reason we did back there. So I'm just going to say C steps 5 and 6. And actually we could go 5, 6, and 7. We can now say that Q equals 2 times some number. So I'm going to pick a different letter, like M. So C, 5, 6, and 7 for number 9. Okay, now we're ready to set up the big contradiction.
That was proving.
Right. So now this is how we create the contradiction. If we take the result of 9, so we're going to substitute the result of 9 and the result of 7 into step 2. So what that creates is it now says root 2 is equal P is 2K, Q is 2M, and that's the contradiction. Yep. That's not insane. That's pretty short.
That's short?
Yes.
Oh, no.
Now, are you guys going to be writing before you have a free? Okay. So now, because of this, okay, the contradiction, this contradicts the assumption we made in root 2 cannot be written as a relatively prime ratio. Cannot be written as a relatively prime or irreducible fraction. Relatively prime ratio. Okay, and the reason is the ratio shares a common factor of 2. The fraction or the ratio 2k over 2m shares a common factor. That's the contradiction. Okay, so our assumption then is incorrect. Okay, So this statement right here contradicts number 1. Therefore, our assuming 1 is true means it can't be true because it leads to something that's nonsense. Okay. Okay, so those 3 dots stands for QED, which is an acronym in Latin. I'd have to look it up again what it is, but it basically means it has been shown. Okay? It has been shown that our assumption is wrong, therefore the square root of 2 is irrational. Okay, our assumption is untrue, therefore the square root of 2 is irrational. Now, at first, you know, like at your age, when I had to do, if I was doing a proof, they were a real drag. I didn't enjoy it at all. Later on, as I got a little older, and we'd sit around with like classmates in college and trying to prove something, it was actually kind of fun because it was like a puzzle. And you're just trying to get from one assumption to a next and to show that something was correct. But, you know, initially it was like, oh, I hate proofs. I hate them in geometry, blah, blah, blah. Okay, all right, let's not bash geometry. Hey, by the way, what did the acorn say? What did the acorn say when he grew up to become a mighty oak tree? Gee, I'm a tree. What do you call a mermaid's undergarment? What do you call a mermaid's undergarment? Algebra. Algebra. All right. So you want to prove we're going to do this by contradiction. Okay. So my first statement is going to be, well, if n squared even, then n is odd. Okay, so I'm going to say suppose n squared is even, okay, but n is odd. What happens when we do that? So n is odd. Okay. Okay, that's our, we state the reverse of what we're trying to prove. All right. So, how can you write an odd number? 2 times some number plus 1. All right, so your second statement could now be this. Okay, well, if n is odd, then n is going to equal 2 times some number plus 1. That's what makes odd numbers. Okay, odd numbers are an odd number is equal to 2 times some integer plus 1. Okay. All right. Now what? So we're saying that if n is odd, we're going to create some sort of contradiction in our statement. So what do you think you would try? What would be the next thing you'd approach? Okay, so let's see what happens when we get n squared. Okay, so n squared would equal 2k plus 1 times 2k plus 1. All right, multiply that out, see where it takes you. So 4k squared plus 2k plus 2k plus 1. Okay, now, is there a way that you can manipulate that polynomial there to show a contradiction of what we did above? Our statement is if n squared is even, then n is odd. And we start with, okay, n's odd. What kind of number is n squared going to be based on that equation? Pardon me? Is there a way to rewrite that equation so that it is purely a multiple of 2, or 2 times some number plus 1? So what you're trying to do here is, if you can establish this, that 2 is equal to some integer, then some integer, then we could conclude that n squared is even. That would not create a contradiction. Okay? But is there a way to do that, or is there a way to rewrite that expression so that it's 2 times some number plus 1? And if that's the case, then n squared would be an odd number, which would contradict number 1. It would contradict this statement that, hey, n squared's even. So look at that 4k squared plus 4k plus 1. Is there a way to rearrange it, group and factor it, so that you get one of those? Yes?
That's not supposed to be odd, and then it cannot be divisible by 2, right? They would all have to have not have a common factor.
If a number is odd, it can be written as 2 times a value plus 1. Okay, so odds and even, I'm not sure I understand your question. Say it one more time.
So if an odd is, so if n squared, so n times n, that's odd and cannot be divisible by 2.
If a number is odd, it's not divisible by 2. That's correct.
The equation represents.
You're right. That equation is not divisible by 2 because you can't divide 1 by 2 evenly. Okay, so n squared But is there a way to write that in the form that makes it an odd, that allows us to say it's odd? Yes.
Do you like square rooting?
No, you don't have to. You could, but you don't have to. Okay, here's a hint. Group the first two terms. Can you factor anything out? Okay, or I could factor out a 2. And if I just did the 2, I can factor out 4k, I can factor out 2k. Okay, but if I took out the 2, I would have 2k squared plus 2k plus 1. So this is 2 times some integer. If I multiplied those out, that would be some integer plus 1. So what this allows me to conclude is n squared is odd, because I can write it in the form of an odd number. Well, if it's odd, that contradicts our original statement that it has to be even. Okay? So this is impossible. Because we assumed n squared is even in number 1. Therefore, n cannot be odd, and it has to be even. And there's your proof. So try your hand at the last one. If you're told that that's odd, then n has to be an even number. So what would you start by assuming? Odd. Right, yeah, you're switching your conclusion. So if n cubed plus 5 is odd, then n is odd. So we took this part and we wrote the opposite of it. Okay? So where would you work towards to create a contradiction? If you start off with n being odd, then n is going to be 2 times some number plus 1. That's what makes a number odd. Now, what are you going to do with that to create a contradiction? Yeah, and try to make it equal to what? And show that it's equal to what? Right, right. So here's your strategy. Okay, so your game plan here to use a proof by contradiction is to substitute 2k plus 1 into n cubed plus 5 and show that it is even. Yes. Yes. Okay, that's your goal. So what's that next line going to look like? Yeah, so 2k plus 1 cubed, where am I? Plus 5. All right, now to expand a number. Okay, so we've expanded this binomial here. So that's this right here. If you took 2k plus 1 times 2k plus 1 times 2k plus 1. So that's what we did. Did it on another sheet. This would be 2k plus 1 times 2k plus 1. Okay, that's 2k plus 1 cubed. And if you multiplied all that out, it would become this. All right, now, when we add 5 to that, we get statement 5. Okay? Now, statement 5, if you look at it, all the terms have a common, have 2 as a common factor. So I could rewrite this as 2 times 4k cubed plus 2k squared, whoops, plus 6k squared plus 3k plus 3. So I've established that this has to be an even number because 2, I'll be right with you, 2 times an even number, okay, and this, this is just a number. 2 times some number is going to make an even. Let me fix that. Just a second. Okay, 2 times some number and this in the parentheses is some number. That means that this whole expression is in even. So we can conclude here that n cubed plus 5, since it equals this, it has to be an even number. So this, which is 4k cubed plus 6k squared plus 3k plus 3. All right. That is some number multiplied by 2. That makes it even. So n cubed plus 5 is even, which contradicts our assumption. So here's the contradiction between that statement and this statement. Okay, so I'm making a recording right now, so I'll be done in just a second. All right, so n cubed plus 5 being even contradicts n cubed plus 5 being odd. Therefore, our assumption that n is odd is false. Is impossible. Therefore, n is even. So, n is even. Alrighty.